Okay, so while you're moving, I want to let me give you the setup here. So the year is 2799, and you are climatologists trying to find out exactly what the tipping point was for global warming. And you think it was sometime around the summer of 2009, but you're not quite sure. You're trying to figure out exactly what happened. Baltimore seemed to be important, with the harbor flooding and everything like. Unfortunately, you have no weather records from the time because they were all destroyed in the flood. But you do turn up a diary of mine from the summer of 2009 in which I recorded how much ice cream I ate every day. And from this, you want to reconstruct the weather patterns. Okay. So we're going to see how to do this using some statistical techniques. We're going to be doing unsupervised learning, which is kind of fun. So let's start out by making some assumptions, because when you're doing modeling, you always make assumptions, right? And the assumptions are never right. They're just better or worse. They're what you can get away with, because you'll never know the truth. Okay, so we're going to assume, first of all, that on a cold day, so probability given cold, I am 70% likely to eat one ice cream. Can you see where I have the cursor here? 70% likely to eat one ice cream, 20% to eat two ice creams, and 10% to eat three ice creams. Okay, so 70, 20, 10. And on a hot day, it's the other way around. 10, 20, 70. Okay. So I'm just more likely to eat ice cream on hot days. And other things equal, if you see that I ate one ice cream, the odds are 7 to 1 that it was a cold day. If you see that I ate three ice creams, the odds were 7 to 1 that it was a hot day. And if you saw in my diary that I ate two ice creams, it's even Steven. Okay. Other things equal. But other things aren't equal. Okay. There's also some inertia to the weather. So here we say, again, this is what happens if it's cold. This is the probability that the next day is cold. 80% likely that the next day is cold. We're going to assume, again, this is just an assumption, 10% likely that the next day is hot. And on a hot day, it's the other way around. Okay, so cold days tend to be followed by cold days, and hot days tend to be followed by hot days. Okay, that's the assumption. And weather really is more or less like that. Except, since it's 800 years later, we're not sure whether weather was exactly like that back in 2009. We're just going to use that as our starting assumption. We also have some boundary conditions. So we don't know whether this start is like beginning of sentence. So on the first day, we don't know, sorry, on the 0th day, we don't know whether the next day, the first day, is going to be cold or hot. In other words, am I more likely to start my diary on a hot day or a cold day? A priori, we don't know. Okay, so let's just assume I'm equally likely to do either. And also, where am I likely to stop the diary? That's like the end of sentence symbol we had before. So the probability, if it's a cold day, that I lose my diary, so we stop, is 10%. And the probability if it's a hot day, there's also a 10% chance that I lose my diary. Okay? And I never lose my diary immediately, or I guess you wouldn't have found it. It would have just been an empty book. Okay? So is this clear, this set of assumptions? This first thing here is sometimes called emission probabilities. It's saying on a cold or a hot day, it should be called ingestion probabilities, I guess, but in the jargon, I'm not eating the ice cream. The model is producing the diary entry, so we're emitting a diary entry on a hot or a cold day. And this is sometimes called transition probabilities. So am I likely to go from a hot day to a cold day, from a cold day to a hot day, from beginning of sentence or end of sentence to a hot or a cold day. Okay, clear enough? Okay, that's the assumptions. So now, given that, we're able to get this weather reconstruction. Actually, let me just show you a little more here. This is a picture of how many ice creams I eat each day. These are in red. 2 ice creams on the first day, 3 on the second, 3 on the third. So given that and these assumptions, we're able to reconstruct this rather cool graph. So this blue line is how many ice creams I had on each day. Notice that these are integer valued, 1, 2, or 3. And this pink line is the probability that it was a hot day according to the model that I just outlined, according to those assumptions in red. Okay? So what this reconstruction is showing us, you don't know yet how we got the reconstruction. Let's just look at it first. What the reconstruction is showing us is that there was kind of a hot spell here where I tended to eat a lot of ice cream, and then a cold spell in the middle of the summer where I tended to eat less ice cream, and then a hot spell toward the end. So this is actually kind of interesting to look at. What is What's interesting is that, like on a 2 ice cream day, sometimes the 2 ice cream days are being tagged as hot, and sometimes they're being sometimes the 2 ice cream days, like over here, are being tagged as cold. Right? So why is that actually? Yeah, like the previous days. Actually, it can't quite be that, only that, because here the very first day doesn't have a previous day, yet we tagged it as hot. So I thought we said that a 2 ice cream day was equally likely to happen on hot or cold. Yeah, well, the next 2 days, there's good evidence that they're hot. So it would be unlikely that the first day would have been cold, because then we would have had to shift from cold to hot, which is unlikely. So it's more likely that the first day was hot, consistent with the future. So this model, despite the fact that these conditional probabilities don't look symmetric, it's probability of the next day given this day, the model is actually symmetric in the sense that the reconstruction is going to be looking both at the past and at the future in order to give you the most likely set of the most likely set of weather tags here. So somebody mentioned before part of speech tagging. How's this problem like part of speech tagging? So in part of speech tagging, you have a sequence of words, and for every word, you have to assign a part of speech to it, like noun or verb or determiner. So in this case, what are the words? It's the number of ice creams, right? That's what we observe. And the hidden thing that we're trying to reconstruct, instead of part of speech tags, we have weather tags. And instead of having 40 or 50 of them, we only have 2, hot and cold, because that will make it possible to actually visualize this. So it's I've stripped down the problem to only 3 words and only 2 part of speech tags. Plus, start and end are like the special beginning of sentence and end of sentence words. Or do I want to say that those are words or tags? Maybe I should say that they're special tags. OK, so how did we get this graph? We did it by considering all possible tag sequences. So there are 33 days in the diary. So how many possible tag sequences are there? 2 to the 33rd, quite a lot. Each one of those is a path in this graph. So this is the path hot, hot, cold. This is the path cold, cold, cold. So how likely is each of these paths? Well, what's the probability of hot, hot, cold? So let me explain what this graph means. This state here, if we come to this state, this means that the first day was hot. Think of this state as representing midnight at the end of the first day. Okay, and it records whether that day was hot or cold. So hot, hot, cold. The first day was a hot day. We end up at the hot state at midnight. Second day was a hot day. Third day was a cold day. And this here is the intervening day. This arc here is the intervening day between the 2 midnights. So the first day, we want to know there's some cost. The first day could be either hot or cold. We decided to choose hot. We had 0.5 chance of picking hot and 0.5 chance of picking cold, given that the previous day was start. That's different here. Here, if we're at a hot state, probability that the next day will be hot is 0.8. Probability that the next day will be cold is only 0.1. So here, when we choose whether to go to hot or cold, we're more likely to choose hot. This is a higher probability. Paths that involve this arc are higher probability paths. There's another reason that this arc is more likely than that arc. On the second day, we have to decide not only whether it's going to be a hot or a cold day, but given that choice, how many ice creams to eat. Okay. So when I say we have to decide, what I mean is something like, the world decides, God decides what the weather will be. Somebody decides randomly what the weather will be and how many ice creams get eaten. Okay. Maybe God decides the weather and I decide the ice creams. So this is saying, OK, 80% chance that it's a hot day, and then 70% chance that we decide to eat 3 ice creams. This is saying 10% chance that it's a cold day, given that the previous day is hot. And then once I've decided it's a cold day, what's the chance that I would eat 3 ice creams? Only 10%. Okay? So there are other choices that could have happened, right? So I've only shown, I've shown it being a hot day or a cold day. I've only showed the cases where I eat 3 ice creams. I didn't show the other choices of eating 1 or 2 ice creams, because they didn't happen. We don't have to put them in the graph. We're only concerned about paths that actually explain the data that we observed. Okay. So this is an arc that explains why I ate 3 ice creams. It was a hot day and I chose to eat 3 ice creams. Pretty likely. 0.8 times 0.7. This alternative arc is another way of explaining why I ate 3 ice creams. It was a cold day and I ate 3 ice creams. Both those things are unlikely. So this is an unlikely arc, 0.01 versus 0.56. Okay? So we prefer this arc, other things equal. But other things might not be equal, because in order to take this arc, we needed to take other arcs that would get here and other arcs that would get away from here. So that's kind of the insight, is we're interested in looking at all of the paths. The probability of a path is the probability of all of the weather events and all of the ice cream events necessary to make that path true. Okay? So there's 2 to the 33rd paths. So if we're interested in knowing whether the second day was hot, we want to know whether we went through this state, h at the end of the second day. Okay, that's what we want to know. So of the 2 to the 33rd paths, how many go through here? I think I heard it. 2. More than 2. So here's one, here's another, here. So once we get, it's true that there's only 2 paths that come to here. But there's paths that go away also. So there's actually a lot of paths that go through here. 2 to the 32, actually. So there's 2 to the 33 paths, so about 8 trillion. Right? And half of them go through this, and half of them go through that. So does that mean that the probability we go through here is a half? No, because the paths that go through here may be, on average, more likely than the paths that go through here. Okay? So what we're interested in is the total probability of all paths that go through this state and the total probability of all paths that go through that state. Okay? Well, that's not too bad. So we add up 4 trillion paths here and 4 trillion paths there, and we're done. And you could actually do that. Just be slow. So can we find a faster way? Okay. So what we're interested in knowing is, maybe 70% of the... Actually, let's just take a moment and think about what these numbers are. So what's the probability of the first 3 days being hot, hot, cold? Given the evidence that we've... what's the... Excuse me. What's the product of these 3 arcs? Let's just start there. So we've got 0.1 times 0.56 times 0.01. Now, that is actually fairly likely outcome for the first 3 days. The most likely path is hot, hot, hot. It's 0.1 times 0.56 times 0.56. Still seems pretty unlikely. So why is it so unlikely? Hi guys, sorry we didn't quite wait for you. So what's the, why is it that these paths are unlikely? The paths are not only predicting possible weather sequences, remember. They're predicting weather sequences and the ice cream that I ate. So there's 8 possibilities for the first 3 days, and you can see all the paths there. Each of those paths, its probability is a different way of eating 2 followed by 3 followed by 3 ice creams, which is in fact what I ate on the first 3 days. So over here we have 2, 3, and 3 ice creams. So if we add up these 8 paths, all we get is we've divided all my ways of eating 2, 3, 3 into 8 possibilities, just as we divided up horses into a lot of possible ways of getting horses. They're mutually exclusive. We add up the probabilities, and that gives the probability of eating 2, 3, 3 ice creams. There are a lot of other choices of ice creams, like 1, 1, 1, and 1, 1, 2, and 1, 1, 3, and 1, 2, 1, and 1, 2, 2, and 1, 2, yeah, and so on. This is only, the total probability of these paths is only the probability that I ate that set of ice creams. But given that I ate that set of ice creams, we're interested in which of these paths was the best way of explaining it. Okay? That happens to be hot, hot, hot. So if we wanted to know whether I ate, whether the second day was hot, whether we ended up at this state, so we can look at the total probability of all paths that go through here, which will be very small, because each of them explains the entire diary, with the additional requirement that the second day be cold. And we look at the total probability of all of these, which is also very small, explains the whole diary, with the additional requirement that the second day be hot. And maybe this is the total probability of paths that go through here is 100 times greater than the total probability of paths that go through there. So then it would be, then the probability of the second day being hot would be 100 times as great. as the second day being cold. All right. So how can we do this efficiently? Well, I've given you a little hint with the numbers that we've written here. So the basic idea is that if we want to know how many paths come through here, let's start out by looking at the total probability of all paths that come to this state. Okay. Actually, let's look over here. Probably a little easier. We've got more stuff to the left to look at. So if we want to know the total probability of all paths that come to here, where every path's probability is the product of its arcs, there's two ways that you can get here, right? You can take a flight through here or a flight through there. Okay, there's only two routes. Okay. Well, of course, to get here, there are two ways to do it, and to get here, there are two ways to do it. Okay. But let's put that off for a moment. Once we get here, the total probability of all paths here is the total probability of paths coming through here. We'll call that alpha, times the cost of getting from here to here. Right? So that's all paths that get to here via this. Okay. So it's alpha at this state, total probability of all paths to here, times 0.56, plus the total probability of all paths to here that come through here, which is alpha here times 0.07. Okay. Clear enough? So the idea is we can get alpha here if we know the alphas here and here. How did we get alpha here? By knowing the alphas from here and here. How did we get alpha here? Well, that's easy, okay, because we're only coming from start. So this is our base case. Total probability of all paths here is 0.01. Similarly over here, so that's alpha is 0.01. Now let's work forward. Over here we've got probability of getting here is 0.01 times 0.01 times the cost of, let's start over here. 0.01, this alpha, total probability of paths here, times 0.07, that's this, plus this 0.01 times 0.56, so the paths coming from here, and that's 0.063. And similarly, total probability of all paths there is 0.009. Now we also have, at this state, if we want to know the total probability of all paths here, we take that 0.009 and we multiply it by 0.07. And we take this 0.063, so the sum of those two paths, this one and that one is 0.063. We multiply by 0.56, we get that. And so we find 0.036. Okay. So let's see how we actually computed this on the spreadsheet, because we used it to compute the graph before. Okay. So here we have, okay, so here are the alpha numbers for the cold state. We have 0.01, 0.009, 0.00135. And you saw this, these are exactly the numbers you saw in the diagram a moment ago. And what's happening to these numbers as we go down? They're getting much, much smaller. How come? Well, we're multiplying, which makes things smaller, but we're also adding. I mean, we're adding a lot of paths together. So it's not obvious right away that they should get smaller. It's going to get smaller, right? But remember that at every stage, not only are we multiplying, but we're also adding. So there's you add the thing from the cold state and the thing from the hot state.
But the odds are getting smaller.
Okay, how come?
Well, because we're choosing what is smaller.
Okay, but we're in some sense we're not choosing between hot and cold, right? Because we're adding those possibilities together. So this I think is the same answer I just gave a moment ago. So over here, when we ask about the alpha here, we're considering both the hot and cold possibilities here. We consider going through here and going through here. So the numbers are getting smaller. We are making some choice, but we're not choosing the weather. We're considering the specific set of ice cream, right? If we left out this second factor each time, then we'd just be asking, okay, if we didn't know anything about ice cream, how many weather patterns would there be? What would the chance be of being hot on day 5? What would the chance be of cold on day 5, given that we started at start? And those would be like, 0.7, 0.3, or 0.4, 0.6, or something like that. They would add up to 1. But we're not asking anything like, are we hot at the end of day 3? We're asking, are we hot at the end of day 3 and we've eaten 3 ice creams? Okay, and it's those numbers which getting multiplied in makes a difference. Is that clear? You think? Stick with it, because we're gonna keep looking at this concretely.
Well, I missed the beginning, that's why I don't know anything about the ice cream.
I'm sorry. Okay. I wish I had time to restart.
Okay, doesn't matter.
Okay, so if we look at the formula for computing this is kind of fun. Double click on this, and you see it depends on the alpha cold and alpha hot the previous day, and the number of ice creams on this day. Those are color coded with this formula. And this index thing here is just looking up a probability in the table over here. So that's all it's doing, is it's looking up those probabilities. Okay. So these numbers go down as we generate more ice creams. This is the probability of being total probability of all paths to the cold state, total probability of all paths to the hot state on day 1, 2, 3, 4, 5, and so on.
Excuse me.
Yeah.
Day 13 seems to have a slightly lower probability.
Day 13.
Yeah.
Where are you talking about?
For the alpha probability.
Over this?
Yeah.
Slightly lower. Oh, yeah, this is possible.
Yeah, I know.
Yeah. What I'm saying is that the general trend is going down. So I think what you're saying here is that day 14 actually goes up from day 13, right? Which is kind of interesting. And this is showing that the effect of adding things together actually does make a difference sometimes. You don't always have to go down. Okay. So you might interpret this as saying that day 14 really, really thinks it should be cold, or something like that. That would be approximate, but I mean the reason is this one ice cream. We have this series of it's because of this one ice cream day here. Remember over here we're only looking at the past so far. Okay? Each one here is dependent on what's happened, the number of ice creams on this day and the alphas at previous days. So we're not looking at the future. But remember, I showed you over here that here we were being biased by looking at the future, and I argued that that was the right thing to do. Over here, the fact that we're probably hot on the first day is because we see ourselves eating a lot of ice cream on subsequent days.
I think this also represents a shift between the hot trend and cold.
Between hot
and cold days.
So there is a difference between hot and cold days, sure.
Yeah.
And it's true that more ice cream days tend to be hot, and
Well, I mean, after
yeah.
day 15, actually, it goes to the cold days.
So you're right that that's true in this graph, but this graph is not showing those alpha probabilities.
Oh.
So we'll come to it in a minute. So what I want to argue here is that even though the alphas are not looking at the future, right, we do want to look at the future, and we need to do that for this. So remember, when we looked at this, this picture here, just sometimes called a trellis, when we looked at this picture, we had we were interested in the total probability of paths going through here, and all we've talked about is the total probability of paths coming to here. We haven't looked at the part going away. So in some sense, we've said something like, well, given all the ice creams we've seen so far, do we think this could be a cold day? But we should also be looking at ice creams in the future. So there may have been a cheap path to getting here, but no cheap path for getting away. So is there an analogy to this in, say, part of speech tagging, where you'd want to look at the future? So suppose I say, I can tuna. Okay. Given the left context, beginning of sentence, I, the next word can sounds like an auxiliary verb, like I can do that. Okay. Maybe it doesn't sound like it, but it looks like it when there's can versus can. But when it's written, it certainly looks like it. Okay. But so if you were just going from left to right, you would say I, good, that's a pronoun. Can, good, that's an auxiliary verb. And then you'd be stuck because tuna is not a very good thing to follow an auxiliary verb. Okay. So that's a case where maybe it's cheap to get to that state, namely auxiliary verb, but then you can't make progress. It's very unlikely to generate the rest of the ice creams, the rest of the words, as you continue forward. Okay? So we need to take both into account. So this is actually not so hard. We computed alpha, the total probability of all probabilities to this state. We also want beta, which is the total probability of all paths from this state that get you to the end. And you do that in much the same way. So let's just see it on the spreadsheet. So here, it's going to be a little hard to see, unfortunately, because of this word wrap business. Let's go over here. OK, right. So you can see that beta cold on day 11 depends on the betas for the day afterward. So if you want to know on day 11 what the total probability is of all paths from there to the end, you say, well, we have to go through here or through here. So let's look at the beta here, total probability of paths from here to the end, multiplied by this arc. Total probability of paths from here to the end, multiplied by this arc. So that's all we're doing here. So it's completely symmetric to the alpha computation. It's just in additional columns of the spreadsheet. So if we know how to get the total probability from the start to a node, then we should also be able to know total probability getting from the end to the node, working backwards. OK, well now, here's the interesting question. What we were interested in was the total probability of all paths through a node. So how do we get that? We've got alpha coming to the node and beta coming from the node and erasers behind the node. So let's write down what we actually want. We have this state here. We want to know the total probability of all paths through the state. Well, we've got for this state here, we have 2 squared paths coming to it, and we have 2 to the 30th paths going away from it. So that's 2 to the 32 paths going through it. So let's look at these paths. Here we have 2 to the 2 paths. I won't show all of them, going from start to it, and 2 to the 30 paths going from it to the end. So let's label these paths with names just to see what's going on. So this is x, y, z, and p, q, r. So we're interested in, well, so one path that goes through this state is x times p. So we can come in by x and leave by p. And another path is xq. And another path is xr. And another path is yp, yq, yr, zp, zq, zr. And for those of you who can't see behind here, it's exactly what you would expect. OK, so can we factor this? This factoring trick is the whole idea here. So we've got 9 paths, well, 2 squared times 2 to the 30th paths here. So this is just going to be x plus y plus z times p plus q plus r. Right? Here's all the ways of getting in and all the ways of getting out. Okay. Well, this is a sum of 2 squared things. I've only shown 3 of them. And this is a sum 2 to the 30th things. But we've computed this, right? This is alpha. It's the total number of ways of getting to that airport. This is 2 to the 30th number of ways of getting, or sorry, total probability of paths getting away from that airport. If we multiply these, we have the total probability of all paths through the airport. So it's just alpha times beta. Cool. So let's see how that comes out on the spreadsheet. So here we have the alpha column, alpha columns for the going through the cold state and going through the hot state. Beta column similarly. And now here's alpha times beta. So this is the total probability of all paths going through the cold state at day 1, 2, 3, 4. Total probability of all paths going through the hot state at days 1, 2, 3, 4. Now if you look at the alphas, these tend to decrease as you go down the column, right? If you look at the betas, these tend to Interesting. Well, we're working backwards, so it's not too surprising. They tend to decrease as you go up the column. Right? Because the paths get, as you go up the column, the paths from day 13, then 12, then 11 to the end get longer and longer. Okay, so we're explaining more and more ice creams. When we multiply alpha by beta, we're explaining all the ice creams. So now, this is, say, all the paths that go through the cold state on day 5, 2 to the 32nd paths. Here's another 2 to the 32nd paths that go through the hot state on day 5. Let's add those together, and we'll have the total probability of all 2 to the 33rd paths. There it is. What's going on in this column? Total probability of all 2 to the 33rd paths is always the same, right? It's just a question of how we divided it up. So here, we could look at 2 to the 33rd that go through this state versus that state, or that go through this state versus that state. Okay, and it's different divisions of the paths. So here, you know, we've taken, say, paths A and B and C and D. Here it's going to be A and C and B and D. Okay, but however we divide it up into two groups, the total probability of all the paths will be the same. Now, what do you think it means that this number is about 100 times more likely than that number? 100 times bigger than that number. They're all unlikely, right? Actually, what is this 9 times 10 to the minus 19th? What is this number? What does it represent? Yeah. Yeah, it's the likelihood of that ice cream diary, right? The likelihood of that sequence of choices. So what do you think it means that that's about 100 times more than that? Sorry? Hot day, yeah. What it means is that there's a lot more probability on paths that go through the hot state on day 3 than on the cold state on day 3. So all the 2 to the 33rd ways to explain how I ate those ice creams, the half on which it's a hot day on day 3 have much more total probability than the half for which it's a cold day on day 3. Okay? And that is how we got the graph. So if you look at, this is the probability that we're going to a cold state, in other words, that it was a cold day, and that is the ratio of this to the total. And over here, we have the ratio of that to the total. So these two numbers sum to 1 because we're just asking about of the total of these two numbers. Here's the total. What fraction of it goes to the cold state and what fraction goes to the hot state? So it's about 1% versus 99%. And if we look at this picture, we see that's what we get here. Day 3, it's 99%. Okay, so that's exactly where the graph came from. All right, so let me just ask a little question here. We know now why this day here was tagged as was tagged as a hot day, despite having an apparently uncertain 2 ice creams. It was because of the beta probability, right? Because the beta probability allows it to look forward. If we decide to make this hot, it's more pleasant to express, you know, it's no more pleasant to explain the 2 ice creams here, but it's more pleasant to predict the weather that would explain the subsequent data. Okay. How about over here? We've got day 11. Day 11 is a 1 ice cream day, and yet we predicted that it would be hot. So why did we predict that? Why should a 1 ice cream day be hot? I think it's probably right, by the way. Yeah, not just, yeah. So there's 3 ice cream days after it, and there's 3 and 2 ice cream days before it. I mean, we have a lot of evidence that there's hot days before and hot days after. So if we already believe, based on information from the left, that this is probably a hot day, and we already believe, based on information from the right, that this is probably a hot day, what does it do for us if we predict a cold day here? Well, it makes us 7 times more likely to predict the data that we actually observed. So we're doing a better job. If we made this a cold day, we'd be doing a better job by a factor of 7 of predicting a single ice cream. Okay? But what's the cost for that? Oh, it's a terrible cost, right? Because in order to, given that this is probably hot and that's probably hot, what do we have to do? We go from hot to cold and back to hot? Well, that costs us a factor of 8 twice. If hot, hot, hot is 64 times more likely than hot to cold and back to hot. Because these are better by a factor of 8 to 1. So that way overrides the one ice cream decision. We still think it might be cold, right? The probability that this is, we're still getting something on the paths that go through a cold state here, but just a lot less than we would have in a one ice cream day like this, which is surrounded by cold days, and we're pretty sure that it's cold. Okay, so let's do some experiments, because that's why it's fun to do this stuff on a spreadsheet. So what would happen now if we weakened this weather inertia? Actually, let's just totally take this weather inertia away. Okay, so hot days and cold days are equally likely to follow each other. Okay, what does this look like now? Looks like the data. Okay. So in fact, what this is saying, this is 7/8. 7 to 1 probability on a 3 ice cream day that it will be hot. It's exactly this 7 to 1 ratio here. There's no information at all from the surrounding days, because the day before, the day after have nothing to do with the weather on this day. So this looks exactly like a picture of that, just squished down into the 1/8 to 7/8 range instead of the 1 to 3 range. Okay, it's exactly tracking the data. So this is kind of what you'd expect. What would happen if we went to anti-inertia? So we decide, the weather kind of whipsaws. This isn't Earth, it's Venus, or it's Earth after the catastrophe. So after a cold day, it's likely to be a hot day, and after a hot day, it's likely to be a cold day. Okay, now what do we have? Now this is trying very hard to whipsaw. So here, actually, this is rather interesting. We have 3 one ice cream days in a row. It thinks the middle one's probably hot, just because it's trying really hard to alternate. So this is sort of the mirror image of what we had before on day 11, where it preferred hot, 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 and that was 64 times more likely. Here it's saying it prefers cold, hot, cold. That's 64 times more likely than cold, 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 and one ice cream be damned. So it's trying to alternate. Over here, it didn't quite manage to alternate because there's sort of this phase reversal where it couldn't manage to stitch the left half together with the right half by alternating. It was able to alternate much more happily and explain the data, while still kind of explaining the data over here. And over here, similarly, if it took 2 hot days in a row. But it's trying real hard to alternate, just as back in our original setup, it was trying real hard, despite something like this, to keep the same weather. Here it's keeping the same weather, even though there's a 3 ice cream day in the middle of a hot spell. It keeps it in the middle of a cold spell, decides to keep it cold. Okay, so let's try another experiment. Actually, maybe I will, No, let's do it quickly. So what happens if we change this column here so that these are, let's try this. Okay, what's going on here? So now I've said that both cold days and hot days are likely to be followed by hot days. So one thing that certainly happened is that hot days have become more likely. Okay. But how does this relate to this picture up here? There's basically no inertia again. Again, these values here correspond exactly to 1, 2, and 3 ice creams. Because again, we get no evidence from the surrounding weather. It's maybe a little counterintuitive, but think about it for a moment. Here, the probability of a hot day today doesn't depend at all on what the weather was the previous day. Okay. So we get no inertia effect. All right, so we have, let me just undo this here, okay? So we have this reconstruction. This looks pretty nice, right? But there is something fundamentally funny about it. What's funny about it is we claimed here that on cold days, about 20% of the time I'd eat 2 ice creams, and on hot days similarly. Now let's look at the days here that I predicted to be cold. Yeah, it's true that about 20% of the time I'm eating 2 ice creams. But if we look at the days that we predicted to be hot, about 40% of the time I'm eating 2 ice creams. So this number is basically inconsistent with the data. It should be 0.4 according to our own reconstruction. So our own assumptions seem to be undermining themselves. When we use these assumptions, which I just pulled out of my ear, right, to estimate this graph, on the data, the graph then gives us some conclusions which are inconsistent with my original assumptions. So what we'd really like is for them to be consistent. So what do you think we could do? Maybe we should adjust these assumptions. In fact, one reasonable way to adjust the assumptions is to take the probabilities that we estimated here and put them back into the table. So we'll see how to do that in a minute, but first I want to show you the results. So as we scroll right on the spreadsheet, I've got another graph where I've updated the probabilities based on what we saw on the previous graph. On the previous graph, 42% of the 2 ice cream days, of the hot ice cream days, given hot, were 2 ice cream days. And still about 20% of the cold ice cream days were 2 ice cream days. So now I get a new reconstruction. So that's kind of interesting. The picture is actually a little different. Okay. All these numbers kind of changed, actually. So now we used to think that we were equally likely to have a cold day or a hot day at the start of the diary. Now we're pretty sure that it was a hot day at the start of the diary. Okay, because when we go left here, we see, look, it probably was a hot day at the start of the diary. And so we took those things and we fed them back in, and we got a new picture. Okay. So you might wonder why this isn't circular. And the reason is that we're taking the output of the model and we're feeding it back in. How could it learn anything? And the answer is that the data come into it. Okay, so what we're getting is a compromise between the model and the data. The model is making some predictions conditioned on the data. So we know how many ice creams. We're reconstructing the weather from that. The original model was inconsistent with the data. By feeding the results of the model back in to get a new model, we're getting something which is more consistent. It's still not perfectly consistent. And you can imagine, you can salivate thinking about what we're going to do about that. But first I want to show you how we got these numbers. Actually, before we do that, let's just look at the differences between these here. So, no, we probably don't have time to do that. OK, so let's look at the computation here of how we figured out how we got those new numbers. So we said, OK, on day 3, we had a 1% chance of it being a cold day and a 99% chance of it being a hot day. Now we know that it's a 3 ice cream day. We know that. So we believe that we have, actually, before I do this, let me give you an intuition. I'm sorry. So when we did this re-estimation, over here, day 27 is being counted as like 50% likely to be hot, 50% likely to be cold. So I said before we were interested in the fraction of 2 ice cream days, of hot days and cold days according to this graph that were 2 ice cream days. Do you think we counted day 27 as a hot day or a cold day when we were computing these numbers over here? Was that a 2 ice cream hot day or a 2 ice cream cold day? What would be the right thing to do? You can throw it out, but then you'd be throwing everything out because none of these are like clearly hot or cold.
Weight the observation by the probability.
Yeah, right. So we say, let's count it as half of each. Okay? So if you were trying to, this is like figuring out how many pizzas you're going to get at a party. Right? So if you invite 10 people to a party, if 7 of them RSVP yes and 3 RSVP no, then you order pizzas for 7 people. But if all of them RSVP, oh, I have a 70% chance of coming or something like that, then you still order 7 pizzas, right? So we're just guessing, whether this is likely to be hot or likely to be cold. So this is what I started showing you on the spreadsheet. Let's go to day 27, which we were just talking about. Here we have a 51% chance of it being cold, 51% chance of it being hot. Now, we know that it's a 2 ice cream day. So look at the headers up here. This is the chance of a cold 1 ice cream, cold 2 ice cream, or cold 3 ice cream day. It's definitely a 2 ice cream day, has a 51% chance of being a cold 2 ice cream day. And looking at these hot columns here, it has a 49% chance of being a hot 2 ice cream day. And we know it's definitely not a 1 or a 3 ice cream day because we saw the diary. Okay? So now if we go down to the bottom, I've totaled these up. And you can see that we had a total of about 10 cold 1 ice cream days, 3 cold 2 ice cream days, and 1.5 cold 3 ice cream days. And we just, so that allows us to figure out, right, and sorry, we have a total of about 14.7 cold days period. Okay, so this 0.961 happened to go into the cold 0.961, went into the 2 ice cream column. So in general, all of this 14.7 cold days, they all got divided up between the 1, 2, and 3 ice cream cold days. So now we know what fraction of 1, 2, and 3 ice cream days are cold, just by doing that computation. That's easy to calculate. We see that about 68% of the 14.7 cold days are 1 ice cream days, and about 21% are 2 ice cream, and 10% are 3 ice cream. Okay. So that's how we got these numbers. Okay, so notice that we also re-estimated these probabilities. So let's go back to this graph. So what do you think from this graph? Do you think that by looking at this reconstruction graph, do you think that a hot day is likely to follow another hot day? Looks like it probably is, right? Because we have a lot of things which seem almost sure to be hot days which are in sequence. And hot days seem to be less likely to follow cold days. Nonetheless, I'm going to maintain that this graph is not enough to re-estimate these transition probabilities. These are like bigram probabilities. Right? They're asking whether 2 parts of speech, 2 weather days, are likely to succeed each other. Hot, 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 cold, cold, hot, and cold, cold. Okay. So I'm going to claim that we cannot, from this picture, figure out whether hot days were likely to be followed by hot days. Let me prove it to you. So suppose we make the distribution of ice cream the same on hot and cold days. So at this point, what do we have? It was kind of an interesting experiment. What's going on here? So this is saying cold day, I usually eat 3 ice creams. Hot day, I also usually eat 3 ice creams. What happened to our weather predictions? What's the diary telling us? Anything about the weather? Nothing about the weather. The weather is totally uncorrelated with the number of ice creams, according to these assumptions. Okay. Now, according to this model, if we reconstructed these days, if we look at all the paths, the high probability paths under this model, do the high probability paths tend to have hot days followed by hot days or hot days followed by cold days? What do you think? So this is, with those changes to the ice cream probabilities. Cold, cold is still 8 times less likely than hot, cold. Okay. So paths with a lot of cold, cold on them will actually still be unlikely. So let's see what the model actually believes. I'm going to show you another graph that we haven't looked at before. Unfortunately, the lines are kind of on top of each other here. But there are 4 kinds of lines. At every day, starting with day 2, we ask about the previous day and that day. Okay. So this pink here says it's pretty likely, about a little less than half probability, to be a hot day that was preceded by a hot day. It's also pretty likely to be a cold day that was preceded by a cold day. And if you look very carefully at this, you can see this purple star behind. These two things are unlikely. A cold day followed by a hot day, a hot day preceded by a cold day, or a cold day preceded by a hot day. Those are unlikely, these are likely. Okay? And that's what you would expect from this picture. Okay? The hot arcs are still more likely according to this model. So even though we can't tell what the weather is, we still think hot is more likely than hot-cold. And I'll show you how we reconstruct this in a minute. So let's go now to an alternative, which is what if we have anti-inertia? Okay, well, it's still the case that this is totally flat because the ice cream probabilities are still not correlated. We still left them at exactly the same on cold days and on hot days. Sorry, this is not really working, is it? It's the same on cold days and on hot days. But if we look at these second order probabilities now, the bigram probabilities, we'll see now because the model started out by assuming anti-inertia, these have switched. The yellow and light blue are the probable ones, hot to cold and cold to hot, because that's what the model thinks. The model thinks it should put more probability on the paths that alternate instead of the paths that keep the same weather. Okay? So the point is that this graph is exactly the same both times, but this graph changed. Therefore, we can't get these second order probabilities just by looking at the first order probabilities. We're going to have to do something a little bit different. So let's go back to this picture. What we're interested in is if we look at all of the 2 to the 33rd paths, a quarter go through this arc, a quarter go through that arc, a quarter go through that arc, a quarter go through that arc. If most of the probability goes on paths that go through that arc, then day 3 is probably a cold day preceded by cold. So if we look at the probability of paths going through a particular arc, not just a particular state, then we can see which transitions are likely. Okay. So how do we do that? Well, it's going to be similar to what we had before. So we've got a lot of paths coming into this cold state here, a lot of paths coming out of that cold state here, and we have one arc here which has some cost. So what's the total probability? Let's call that cost, pick a number, x. No, we already have x. We already have p. Let's use a. Oh, actually, yeah, OK. So what's the total probability of all paths going through this arc? Well, we have x times a times p plus x times a times q plus x times a times r, right? Lots of paths coming in, lots of paths going out. If we multiply these individually and sum them, we're going to have 2 to the 31 summands because there's 2 to the 31 paths going through this arc, a quarter of all of them. But fortunately, we have our alpha and beta probabilities, right? So we can say it's just alpha of this state times a times beta of that state. It's the total probability of everything coming in times this arc times total probability of everything going out. So we actually do this on the spreadsheet. So here we have probability of, oh, sorry, let's go back here and change these back to our original numbers. OK, that's our original reconstruction. So now you see that probability of cold to cold, hot to cold, cold to hot, and hot to hot on a particular day sum to 1. So this is how the 2 to the, these 4 cells are how the 2 to the 33rd paths got divided up among the 4 arcs that could happen between day 12 and day 13. That's those numbers, and that's what we're plotting in the graph. And I won't click around the computation, but it's basically just doing this with the alphas and betas that we've already computed. Okay? So this is just a cute dynamic programming trick for being able to avoid summing over 8 trillion paths in order to figure out the weather. The alphas and betas are just a cheap way of doing the computation. The important thing to understand from the math point of view is just we have lots of possible ways of explaining the ice creams. And we're interested in which of those explanations involved day 12 cold and day 13 cold. So how many of what's the total probability of explanations that go across that arc? Okay, so let's look now at the picture that we actually got of the second order probabilities. And it's kind of a neat picture, actually, if I can manage to get the spreadsheet to go over to it. Good. Okay, so there's four kinds of days. There's days where there's days which are hot to hot, and we're pretty sure we have those during the hot spells, and pretty sure that we don't have them during the cold spell. And there are days which are the yellow ones, which are cold to cold. I'm sorry, they're the purple, the dark purple ones, dark purple stars, which are cold to cold, and we're pretty sure we have those only during the cold spells. But look at these other ones, hot to cold and cold to hot. So over here, when the cold spell starts, we are pretty sure that day 14 was a hot to cold day. Okay? And we're pretty sure that either day 27 or day 28 was a cold to hot day, but we're not sure which. Each one individually has probability less than 0.5. What's really going on here is that we think we either had, this is a 2 ice cream day, we think we either have cold, cold, hot, or cold, hot, hot, and we don't know which. So if we were looking at third order probabilities, which you could do, then we'd see that cold, cold, hot, and cold, hot, hot were both likely. Here we're only showing second order, and that doesn't show the correlation between these two. But basically, if this is a cold to hot, then this one probably isn't, and vice versa. I guess they couldn't both be cold to hot. Okay, so let's see now. Let's go back to our flat picture again. Yep. So here we have inertia and no information. Okay. What do you think will happen if we change the probability of starting on a hot day to 0.7? So this 0.5, 0.5 will turn to 0.3, 0.7. What do you think will happen to this graph? We started on, we started on a 2 ice cream day. Right. Sorry, who's talking? I can't see. Yeah, okay. So you think we're going to be 0.7 likely to make the first day a hot day? Yeah, that's probably right. Since we get no information from here anymore. And then what will happen after that? Anyone want to guess? Sorry? Okay, so you think it'll all stay, because of inertia, it will all stay at 0.7. So we think that the rest of the summer is likely to be hot. Okay, so let's see what happens. It's always nice to be able to do experiments. Okay, you were right about the first thing, but not the second. Okay. The reason is that the inertia isn't perfect. You'd be right it would stay at 0.7 if a hot day were 100% likely to be followed by a hot day. Okay? But it's not. So what happens here is, let's look actually at the second order graph, because I think that'll shed some light. So here we're saying this day is, remember this day was likely to be a hot day, but it's also more likely to be a hot to cold day than a cold to hot day. How could it be a cold to hot day? It's probably not a cold day. Okay? So if you're more likely to be hot, remember that whatever you are, you have a 10% chance of switching to the other weather, whatever weather you are. Okay? So the switches are more likely to be, since you're more likely to be hot, the switches are more likely to be in a cold direction. And that's why the weather tends to get colder over time. So this is the current weather. The long-term behavior of this kind of system with some kind of inertia or anti-inertia, the long-term behavior is called the climate. Okay. And any set of transition probabilities will eventually, almost any set, will eventually stabilize like this to some overall weather. So we see here that in the long term, we're about 50% likely to be hot. Even though we happen to have particular, we were 70% likely on the first day, in the long run, we're only 50% because that's what the long-term climate is. So the reason that we don't get this behavior when we actually see the ice creams is we've got some data about that's correlated with the actual weather, so we can reconstruct it. But what this is showing is what would happen if we started a system like this and we generated it using, oh, sorry, I don't want the letter dice. I want the part-of-speech dice now. Generating hot, cold, according to the 0.1, 0.8. And if you try doing it by flipping coins, you'll discover that eventually you will get about half hot and half cold. OK, so now I have an interesting question for you. Oops. So we've done this picture here, which had, right, we've done this picture, which gave us a pretty bad reconstruction of the weather. And we computed the first and second order probabilities. So what do you think will happen when we plug these probabilities back in? So remember, we did these fancy alpha beta computations to be able to re-estimate these probabilities according to the model. OK, let's scroll right and look. So we say we're going to read the emission probabilities off this graph. And the transition probabilities we're going to read off this graph. And that'll give us a new estimate. Here's our new estimate. Looks a little different, actually, doesn't it? So why is that? Why do we have this dip in the middle here and this rise over here again? Well, when we looked at our first order graph before, when we did the re-estimation, we notice that these days here are a little more likely to be hot. And that gives us a little bias toward hot days tending to eat 2 or 3 ice creams. So if hot days are more likely to eat 2 or 3 ice creams, then over here when we have, according to the re-estimated probabilities, over in the middle, when we don't tend to have 2 or 3 ice creams, it probably wasn't a hot day. If it had been a hot day, we would have been more likely to eat 2 or 3 ice creams. So these are less likely to be a hot day. So we start getting this little curve here. OK, what do you think we should do now? Do it again. Great idea. OK, so fortunately, this is a big spreadsheet. So let's just scroll right a little bit more. So here's our first order graph and our second order graph. OK, so now we've re-estimated it. We re-estimate again. We re-estimate again. Probabilities are doing something. I'll just keep doing it for a while. OK, look at that. It learned it. It decided we've got a hot spell at the beginning, cold spell in the middle, and a hot spell at the end. So let's just look up here at the final probabilities that it came up with. So these are rather different from even the ones we started with a different guess. We just gave it a little bias here, right? We gave it a little bias when we started toward the first day being hot. We told it, the weather was completely uncorrelated with ice cream. 0.1, 0.2, 0.7 everywhere. We did tell it there was weather inertia. And from that, it managed to work out some relation completely different from what we started with on those top lines there, with cold days having few ice creams, hot days having many ice creams. And it learned a considerable amount of inertia, more than we initialized it with, between weather days, because you see this actually is very smooth here. It's also damn sure that the first day was hot. We initialized it with only 0.7. OK, so that was fun. So let's do a few more experiments, because The experiments are really what make the spreadsheet fun. So we started out over here at the left by giving it a hint about inertia and no hint about ice cream. Okay, let's do it the other way around. So this is what we started with. I'm going to take away the inertia altogether. Okay, so we start out now, instead of that, funny curve there that was almost flat except at the beginning, we start exactly tracking the training data. But what should we learn from this? So we started out with no inertia. We certainly ought to learn that hot days tend to be followed by, cold days are more likely to be followed by other cold days. Hot days are more likely to be followed by other hot days, because that's what we're seeing here, even in this very bumpy data, which didn't yet know about inertia. So when we move to the right, well, we should see that we've learned a little bit of inertia. And we have, just a little bit. Okay. If we keep scrolling right, this is what we get. Oh, and this is showing the evolution over time. So we started out with it being bumpy, and it ends up smoothing out. Okay. So again, we learned pretty much the same kind of parameters as we did before. We get the same reconstruction, despite having started with rather different initial conditions. OK, let's try a different one. Oops. No, come back. All right. So let's suppose we have inertia. OK, here we've got, just start with this. This is inertia. And let's suppose we have only a slight preference for more ice cream on hot days. OK, so in this case, we start out with this little bump here. Right, so we slightly prefer more ice cream on hot days. And you won't be surprised to see that we learn it. OK, but let's go back here and make it completely get rid of no, I'm sorry. Yeah, OK. Let's kind of get rid of all information by making this completely symmetric. What do you think will happen now? No inertia, no preference for ice cream, nothing going on with start. Everything's totally symmetric. What do you think is going to happen? All paths, by the way, are now, all 2 to the 33rd paths are now equally likely. They all have probability 1 over 2 to the 33rd. So when we re-estimate, what will this picture look like? Will it tend to favor cold days, emitting 1 ice cream, or 2 or 3? It'll still be completely symmetric. It has no way of breaking the symmetry. And that's what we see. This is at just a plateau at 0.5. Okay. So this is at the end, it's exactly the same as it was at the beginning. Okay, so this is one problem you have with this kind of system is if you're symmetric, you'll never get out of the symmetry. So let's break the symmetry slightly and see what happens. OK. So now we get like a little bit of bumpiness here. We have no inertia, right? We've got a little bit of bumpiness. So let's see what happens when we jump over after 10 iterations. Uh-oh. Looks like it didn't work for once. What's going on? OK, trick question. There's nothing fundamentally wrong here. It is going to learn it. But more iterations, yeah. So let's take the result. So here's our final parameters. And stick them back in the at iteration 0 for our new initial parameters. So that'll do another 10 iterations. Do it again. So now we've done 30 iterations, 40 iterations. OK, that's probably enough. Let's look at the end. Oop, it learned it. Oh, but wait a minute. There's something different here. What's different? Yeah, it's upside down. Right. So why did that happen? Yeah, I threw in a little curveball there. I biased it slightly toward more ice cream on cold days instead of hot days, right? Now, the model doesn't know the difference between C and H. You know, as far as it knows the diary, and it doesn't know the difference between 1, 2, and 3. It's just trying to do something where it's trying to find a model which is consistent with the data. It doesn't know whether we're talking about ice creams or hot chocolates. Right? It doesn't know whether I'm eating ice cream or drinking hot chocolate. It doesn't know which way around they should be correlated. It's got these labels C and H. It doesn't know whether C means cold or C is French for chaud, which means warm. Right? So all it's trying to do is predict something. So there's some sense in which this model is as good as the previous model. We just haven't defined that sense yet. So what does it mean for those two outcomes to be equally good? I mean, in some sense, we shouldn't care. In some sense, we should care because it gave us the wrong answer. You know, in fact, I was eating a lot of ice cream at the beginning and end of the summer, and they were, in fact, hot. So it gave us the wrong answer under a particular interpretation of these labels. But heck, this is doing unsupervised learning. We didn't give it any examples of hot and cold days. We just asked it to find some structure in the data. So is there some sense in which we're finding equally good structure upside down and right side up? Well, so we learned two models, right? How do we evaluate models? Think back to the last lecture. Yeah, so does it make good future predictions, right? So we don't actually have another diary, so we don't know whether it assigns high probability to next summer's diary. In fact, it probably won't, and I can show you why it won't. It's because it is really sure that we start on a cold day, not on a hot day, and it'll try to do the same thing next summer. We don't have a lot of data here. It's doing the same thing as looking at one race and saying Paul Revere won, so Paul Revere is going to win next time. Okay? So it's overfitting to the training data. Okay. However, even though it may not predict next summer very well, it is at least predicting this summer very well. So if you ask what the probability is that it's assigning to the training data, this procedure increases it at every iteration. So what's the probability it assigns to the diary? It's the total probability of all 2 to the 33rd paths. And remember, before it was about 9 times 10 to the minus 19th. What is it now after doing all those iterations? Wow, it's about 4 times 10 to the minus 16th. Right? So it's gone up by almost 3 orders of magnitude. So let's oh, can't undo. Okay, hang on. Just go back to the okay, so here we have this picture, right? So we started out with this bumpy thing with no weather inertia, and we learned something. Okay. Let's see what happens to the perplexity over time of the model. Okay. So you'll notice that it's continually going down over 10 iterations. So it starts out saying, well, we have about we have 4 choices at every word, actually. We have we have 1 ice cream, 2 ice creams, 3 ice creams, or stop. And at the beginning, it's not doing a very good job of predicting which ones we actually saw. Its chances are, it's as if it were choosing among about 3.6 equally likely possibilities. But at the end, we get down to better than 1 of 3 equally likely possibilities. So that's the horizontal line 3. So the perplexity by the end has gotten less than 3. And this algorithm, which is called the forward-backward algorithm, it's a special case of something called the expectation maximization algorithm, reconstructs what you don't know at every stage and then it sort of eats its own output until you converge. It's not guaranteed to do well on test data, but it's guaranteed at least to find a local minimum of the perplexity or of the cross entropy. So that means that it's going to improve the probability, its predictions of the training data at every step. And what we see is that it's actually improved it's actually discovered structure in the data. So it's discovered a correlation between hot and cold and ice creams, and between hot and cold in one day and hot and cold on the next day. Okay. So that's the magic of this method. Right. So there are a couple other things I'd want to say, but I'm going to limit myself to just one with a moment of discussion. I want to just do one more little experiment, which is to start with slightly different probabilities. Oh, I'm sorry. Yes. So what I wanted to say is that the right side up and upside down models end up with exactly the same probability of the data. It's completely symmetric if you trade the H and C labels. Right? It makes no difference. Okay, so it's in that sense that the models are equally good. They assign equally high probability to the training data. So I'm going to try a slightly different initialization here, 0.3, 0.3, 0.4, 0.3, 0.4, 0.3. And let's see what happens after 7 iterations. Okay, something funny is happening because it's getting bouncier. So let's take the final parameters and copy them back over. Oops. Copy them back. Oops. Oh, it's not what I wanted either. No. Edit. Paste special. What's the problem? There's something wrong here. Good. Okay. So over time, oh, hang on. It's not what I expected either. Ah, because I need a 0.3 there. Okay. So we start with that. Copy. And back over at iteration 1. Okay. So after several iterations, it gives us this reconstruction. Now this looks very different from what we got before, right? If we look at this picture, we can see it is decreasing the perplexity. It doesn't do quite as well as it did before, so the final result is still greater than 3 after running 40 iterations. Okay. But it did manage to find some structure, so let's look at the structure that it found. Okay. Well, it seems to be that hot days, I shouldn't say hot days, I should say the state H is associated with eating 2 ice creams. And the state C is associated with eating not 2 ice creams. Okay? And we have here something interesting, which is that after an H, I'm unlikely to have another H. So the structure that this discovered is what? What's the structure it discovered in the blue line? H means 2 ice creams. 2 H states are unlikely to be in a row. It discovered that I'm unlikely to eat 2 ice creams 2 days in a row. I can't be moderate for very long. Okay. So that was additional structure in the data that this discovered because we started it at a different point. So in general, the EM algorithm, expectation maximization, you start it somewhere. All it's going to do is find a local minimum of the cross entropy, a local maximum of the probability of the training data. It'll get better and better and better. The answer that you get, so we saw one answer, depends on your starting conditions. We saw one answer where you started, where hot ended up being associated with 1 ice cream, another where hot ended up being associated with 3 ice creams, and finally one where hot ended up being associated with 2 ice creams. They're all possibilities. Suppose there's genuinely 2 kinds of structure. If you had to pick one, you might pick the one where you were interested in the fact, in the, sort of this long-term stability of large amounts versus small amounts of ice creams being explained by H and C. So that's being correlated with the weather. You might also, and that does a good job of predicting the training data. It gets better perplexity. But there's this other structure that we just discovered that I didn't actually intend to put in there when I made up the data, which is that 2 ice creams are unlikely to be followed by another 2 ice cream. And that might also be something good to model. So why do we have to choose between them? They're both structure. Would there be a way to managed to get a model which got an even better perplexity than either of the models we've looked at by getting both this long-term structure and this short-term structure at once. Long-term structure, a lot of ice cream followed by a lot of ice cream for a while. Short-term, 2 ice cream tend not to be followed by 2 ice creams. Would there be a way to get both at once? Yeah, Adam. That's interesting. That let me stay away from that for a moment because the answer is a little bit complicated. There's a more straightforward answer, I think. Yeah, Damianos.
More states?
More states. Why do we just have 2? Right? So we've got one state which is like the long-term. We could, instead of either using our state for long-term weather or for whether we just had 2 ice creams, instead of 2 states, we could have 4 states. 2 times 2. Then we could remember both whether the weather is hot and whether I just had 2 ice creams. Okay? So in general, the more states you have, the more information you can remember about the past. Right? The more distinctions you could make about the past that might help you predict the future. In this model, by only having 2 states, we basically did a lot of backing off. We said, we're only going to remember a little bit, we're only going to remember 1 bit of information about the past, H or C. We left it to the EM algorithm to figure out how to use that bit of information to summarize the past. That's the cool thing about EM. So we said we're going to back off to 1 bit of information, and you figure out what that 1 bit is going to describe. Okay? We only used 1 bit so that it would fit on the spreadsheet, and because we only had 33 days of training data. And if the thing is already overfitting to training data. If we'd given it a lot of states, it really would have overfit and wouldn't have captured good generalizations that would predict the future well. But if we had a lot of data, we certainly should have used more states, just as if you had a large corpus and you're building an n-gram model, you could afford to use a larger n, because you have enough data to actually get the statistics out. Okay. So what was magic about this compared to the first lecture was only that in the first lecture, we assumed that somebody gave us the parts of speech, and here we kind of figured them out. Okay. Good. So time to end. We will meet back at for the afternoon lab across the quad at Schaffer 100 at 1:30. And if you don't have an account yet on the CLSP computing systems, you probably want to show up 10 minutes early to be able to get an account. Okay. Why don't the JHU people put up their hands again so that others know to follow you to lunch? Okay, good. Thanks very much. These, by the way, I got to say one more thing. These are called hidden Markov models. The hidden part, the Markov model is the fact that the weather depends on the weather on previous day or days, and the hidden is that you never actually see the weather. You have to reconstruct it. Thanks for staying late.